RAMs and DSP blocks and networks on chip, other parts of the FPGA that we haven't really gotten to yet. And another paper from Altera, which is the architectural enhancements in Stratix 5. The big new thing in Stratix 5 is Altera introduced using pulse latches instead of registers, which is something they built on in later architectures as well. It allows some interesting area optimizations by making something that's cheaper than a register and some interesting time optimizations. So yeah, so that's like a short sales pitch for reading these papers. Okay, no lecture next week. I'll release assignment 3, which is a little different. Okay, so no more HDL design. This is it's called a RAM mapper. It's a type of CAD algorithm. Basically takes the RAM that is in a circuit and figures out how to map it to the physical RAM that exists on an FPGA chip. You are going to make a CAD program, so a program that can solve that problem. First, apply it to a sample FPGA architecture that's realistic. It's similar to Stratix 4. And then you'll use your RAM mapper to change the architecture of the chip and say, well, this is what I think we should build, right? If I was an FPGA architect, here I'm going to answer some questions about what makes a good RAM architecture on the chip. There are detailed instructions in the assignment, okay, because I'm giving you a pretty bare bones summary. You can write it in any software language you want. So for this one, you're not writing HDL, you're writing software. I don't care what language, doesn't matter. Choose one you're very familiar with. So people often use C++, but some people write it in Python or Java. It's all fine. Well, in the another lecture or two, we'll talk about RAM mapping. I'll probably post the slides for that lecture in advance so you can look at them if you want, because they may help you with some background for this. I'm not going to make the assignment due for quite a while so that we go over that lecture before this is due. But if you're I know during reading week you might be bored. You're like, wait, what am I doing with all this, without assignments, without lecture? I'm sitting here, I'm staring at my cell phone. I don't know what to do with myself. So you could basically go look at this assignment if you wish. On the other hand, if you're like, I really want to stare at my phone for a whole week, I don't want any distractions, or even better, you want to go outside and enjoy the countryside, you don't have to look at it yet. Okay, I'm going to give you quite a while to do it. I'll also release the term or survey paper instructions. So remember, by the end of this course, you have to write a 2,500 to 3,000 word approximately, well, no more than 3,000 words, but it can be less, paper that summarizes some interesting area, something somewhat related to the course. I'll be pretty generous about what's related. So this isn't due for a long time either, right? Even longer. It won't be due till late December, but I'll release it in case you're like, well, I think I'm going to be busy then, or I want to finish the assignments early. So for those of you who'd like to get stuff done early, you can do this anytime. But again, you don't have to do it right now. You've got a long time. So I guess this is the hope that there are some people who do things early. We'll see, right? If no one does anything early, it's still okay. But if you're one of those people, I've given you some options. Okay, so that was a pretty brief overview of those two assignments. Any questions on that? Okay, sounds good. All right, so with that, I'm going to, let's see, maybe there's a question in the chat. Okay, no, that's just the YouTube stuff. Okay, so let me turn off the projector. We're going to go back to the whiteboard or the chalkboard for a while. Let's see. Let's mute that. How did assignment 2 go? Went okay? It's done? No one wants to volunteer an opinion? Okay, I guess we'll see. Hopefully it was not too painful. Quartus licensing is kind of painful. I know some of you have been like frustrated with like, hey, why do I have to select this or that? Trust me, Amin and I are off. Like, we do investigate all those things. So the sysadmin has like this stack of emails from me about, hey, have you tried this with the license? Have you tried that with the license? So anyone who works at Intel, simplifying Quartus licensing would be good. So. Although I don't think AMD is actually substantially different. It just seems to be something the FPGA industry likes to do, like make licensing complicated. Okay, so what we were doing at the end of last week is we're looking at a simplified FPGA. I mean, it's a real FPGA. It's just its architecture is simpler than most of the ones you're going to do commercially these days. But we're building its circuitry so we can see what's inside this thing and get a sense of how much area different things take. before we just start reading papers that talk about architecture trends. We want to have kind of a sense of what's going on. So we built the LUT. Okay, so we built that out of a bunch of SRAM cells and a pass transistor multiplexer and a few inverters and a level restoring circuit. And we found for a 4-input lookup table, we needed 217 minimum width transistor areas. So just the area, including the spacing that you need to make a small transistor. So kind of a layout, process technology independent estimate. This doesn't have any real physical meaning to you yet. Just putting that number up there so you can compare it to some of the other things that we're going to do, right? All that matters is just kind of how big are things compared to each other. We don't really care what this is in square microns. Okay, so we built the LUT. Now we need to connect it to the programmable routing, because that's the other key thing we need to make any reasonable FPGA. So the next thing I want to do, remember the picture of the architecture we were building. It was a 4-input lookup table. It's island style, so surrounded by routing channels. And we need to be able to connect the inputs of this lookup table to those routing channels. Okay? So calling that an input port to the logic block. Logic block in this case is just a LUT. And I want to know how big is that thing. And I'm going to need 4 of them. Okay? But they're all going to be the same. So I'm going to make 4 multiplexers that can be have some SRAM configuration that can be set by the CAD tool to choose, which of the routing wires running by here am I going to connect to this input. And I'll do that for all 4 of them. Does that make sense? So I need to choose how big is this multiplexer. And in order to choose that, I should do some CAD tool studies and so on, figure out how wide my channels are. But a reasonable choice for this, for the architecture that I've just shown you, is about a 16-to-1 mux. Okay, it's not like magic. I could make this work with a 32-to-1 mux. I could make it work with 8-to-1. This is a pretty reasonable choice, probably a little bit more optimized than either of those other choices, but those ones wouldn't be crazy either. Okay, so I need to build that. So see how much room I have here. Okay, so how can I build that? I'm going to build it using pass transistors, just like I did for the lookup table. So it's going to look a lot like the lookup table. What do you think I should do? Any ideas? So what's the simplest way you can think of building this? So I've got pass gates and I've got SRAM cells. I can build it with that. So what's the simplest topology you can think of? I just want a 16-to-1 mux. What do you think? Just make 16 pass transistors and control them with 16 SRAM cells. And my CAD tool is going to put a 1 in one of those SRAM cells and put zeros in all the other ones, and that's going to decide which routing track gets connected. So yeah, that's a good idea. So let's do that. So I'm going to call that a 1-level mux. Okay, so 1 level because there's just 1 level of logic in a sense, 1 level of pass gates. Okay, so I've got a bunch of inputs. These inputs are actually all just routing wires, but I'm just going to label them with numbers. Okay. So I've got a pass gate controlled by an SRAM cell. Got another input that's possibly connected. Just connect it to a pass gate, another SRAM cell. And I said I wanted a 16-to-1 mux. So that's going to keep going till I get to input 15, which is another pass gate with another SRAM cell. Okay, so output of these pass gates, what should I do with them? What do you think? You probably know. Just stick them all together, right? They're all shorted together. So 16 inputs, program a 1 in one of these, zeros in the others. One of these values gets copied to the output, the other 15 are ignored. Okay, they're pass gates. We already saw last week that pass gates don't transmit a logic 1 very well. They degrade it by a threshold voltage. So I want to basically, well, I should put an inverter on here anyway, because I don't want to put a big capacitive load on my pass gate. So I put an inverter to isolate it, and that's not quite enough. I also need to put in this little level restoring circuit where I put in a weak pull-up or a keeper transistor that makes sure that eventually this signal goes all the way to VDD, because otherwise it wouldn't, and this inverter would leak a lot. Is everybody with me on that one? Okay, so the whole point of doing this is I want to see how big it is. So let's first calculate how many transistors it has. Okay, so the number of transistors is just an SRAM cell takes 6 transistors. Okay, the reason is if you look inside an SRAM cell, it's cross-coupled inverters. That's a latch. Each inverter has a pull-up and a pull-down, so that's 4 transistors. And then you put 2 access transistors on it to write it. Okay? So when you want to write this, you put a 1 on one side and a 0 on the other, or a 1 on this side and a 0 on that side. And you make these pass transistors basically stronger than their pull-up transistors so that you can pull one side or the other to 0 of this latch. So that's a basic SRAM design. But what it means is that an SRAM takes 6 transistors, and they can be pretty small. Okay, this is usually a very optimized layout, so I'm going to assume that all of these are minimum size. You have to make the pass gates a little bit more powerful, but the layout's so optimized, I'm just going to ignore that and say it's 6. Well, it is 6 transistors. I'm also going to assume they're really small. Okay, then I need the pass gate. So I've got 1 pass gate. So I've got 6 plus 1 transistors, and I need that for every input. So if I have 16 inputs, I'm going to multiply that by 16. And then on this output, I've got 2 transistors in the inverter, 1 pull-up, so I got 3 more. Okay? All right, so that's 6 SRAM transistors, which are small, and 1 pass transistor, which is bigger. Okay, if I want this to be fast, I'm probably going to make this pass transistor, which is, on my timing path for the routing. Getting this signal from here to here, this is a reasonable amount of metal. It's connecting a bunch of transistors. I probably don't want to make this minimum size because it might get slow. So I'm going to assume I make that a bit bigger. Okay? So how much bigger should I make this pass transistor? To really know, I'd have to do some SPICE simulations and look at how much faster it gets as I make it bigger and how much area it's going to take me. A reasonable value for it, which I'm just going to ask you to take on faith, is say that I make the drive strength of this pass transistor is the 5 times the minimum. Okay? So I want a transistor that's 5 times more drive, 5 times more width, or for FinFETs, 5 times the number of fins of the minimum I could possibly make. Okay, so with all those assumptions, I can now compute my area of all of these transistors. And it's just equal to the 6 SRAM transistors, which are small. So I'm going to count them all as a minimum size transistor. And then we had this fairly simple equation. As we make the drive strength bigger of a transistor, its width or its number of fins gets bigger, but we don't have to increase the spacing around it, so the total area doesn't go up linearly. Well, if I need to make it 5 times more drive strength, I don't need 5 times the area. The equation that I'm using is a nice simple one. I say it's half a unit of area plus the drive strength, which I said is 5 times bigger divided by 2. Okay, so that means this pass transistor is going to take like the area of 3. It's going to have 5 times the drive strength, but take 3 times the area of a really small transistor. Okay, you got to multiply that by my number of inputs, which is 16, because that's what I said I'm going to do. And I'm going to add 3 at the end. Okay? And if I plug in those numbers, I get an area of 147 of these minimum width transistor areas. Okay, so if I compare that back to my lookup table size, it's not as big as my lookup table, but it's, I don't know, about 60% of the size of my lookup table. And I'm going to need 4 of those muxes. So it's showing that my programmable routing is pretty expensive, because this is only part of my programmable routing. Connect the inputs to it. And I'll take 4 of these. I'm going to have 600 units of area, which is almost 3 times the size of my LUT. So somewhat painful, right? Programmable routing is big. Can I make this mux smaller? So clearly it's pretty large. Can I design this in a way where it takes less area? So you could say, well, cut the number of inputs. And I could do that, but it might impact my routability and have other knock-on effects. So if we're running CAD experiments, that would be a good thing to try. But I'm not going to do that. Just can I change the way I build it to make it have the same functionality but take less area? So what do you think? So I'll give you a spoiler. There is a way to do it, right? So one day when I'm near retirement, I'll just start answering questions where there is no answer, asking questions where there is no answer, just to torture the last class that I teach. But you are not that class. So there is a way to do this. So, so I guess think about these SRAM cells. So you can't really do it in less pass transistors. In fact, the alternative topology is going to increase the number of pass transistors. Well, something that's a bit painful about this, every single pass gate has got its own SRAM cell. And that's actually more area than the pass transistor itself. The pass transistor is doing the work. The SRAM cell is just storing state. So, can we do this with fewer SRAM cells? Yeah, what do you think? Make it a 2-level mux. Yeah. Yeah, so that's a really good idea. Okay, so you're saying, don't think of it as a 16-to-1 mux. Build a 4-to-1 mux and then another 4-to-1 mux. And that's the next thing I'm going to do. The trick to that one is also to realize you can share SRAM cells, which I think is where you're going with that. Okay, so hold that thought. That's a very good design, better than the design I'm going to show you. But we're going to go to a halfway step first. Well, another alternative one, but the one you just mentioned is a very good one. So think of the lookup table. The lookup table, we used essentially a binary tree of pass gates. And that was important in the lookup table because we needed each input to control one level, basically, in that big tree. We could build a tree like that here, but control it, instead of with the inputs to a lookup table, we'll control it with SRAM cells. And that actually minimizes the number of SRAM cells we need. So let me show you that one. Okay, so, all right, so let's do a K-level mux. K is like the log base 2 of the number of inputs. Well, -1. Okay, so it's basically like a multi-level mux. Okay, the most levels that you would ever do. So what does that look like? It's unfortunately a little more painstaking to draw. So let me draw this, and it might get a little messy. Okay, so I'm going to assume that I can take both the true and complement value off my SRAM cell. So that's like the state of the cell, and that's the S bar. And for FPGA configuration RAMs, usually you can actually connect a wire to both sides of this, which means I can get both the true and the complement out of the SRAM cell without adding an extra inverter. If I couldn't do that, I'd have to add an extra inverter. But I'm not going to do that. I'll assume that I can get both sides. Does that make sense? So inside the SRAM cell, you always have the true and the complement available. So if I can just wire up to them, I can get both of them. OK, so here's my input 0. And I have to draw a few of these inputs before you can see the pattern. So here's input 1. So this first SRAM cell, if it's a 1, it selects this transistor. Okay. And if it's a 0, it selects this transistor. But that's not. Let me draw another couple of these. Okay, so let's skip over this. And in 3, which is going to come from here. Okay, hopefully that's not too messy. Okay, so if this is a 1, and this actually keeps going down here. So that's going to continue down. This is going to continue down. There's going to be a bunch more transistors down here. Okay, this is the first stage of my MUX. And it's basically, if I got a 1 in this one SRAM cell, I select the upper pass transistor here, the upper pass transistor here, the upper pass transistor here, etc. And it goes onto this wire. If there's a 0 here, I select input 1, input 3, input 5, like all the odd ones, and they make it to essentially the output wire. So I'm just wiring together pairs of pass gates, and one SRAM cell says who makes it to the next level of wiring. Okay? Either the evens make it to the next level of wiring or the odds do, but they don't both make it. Okay, so at this point, I've basically cut my number of signals in half, from 16 down to 8. So there'll be 8 of these intermediate wires. And then I just repeat the same style. So I take that, put it into a pass gate, take this, put it into a pass gate. We have 6 more down here that I'm not going to draw. And I make another SRAM cell. And that SRAM cell controls that one. And it goes down here to control some more. And the complement signal is going to go over here and control this one. Okay, so let's see. And so on. And this signal also goes down here. Okay, so does that make sense? So I just repeat this. If this is a 1, I select the upper transistors. Well, there'll be upper transistor of this pair, upper transistor of this pair, etc. I wire pairs together. So after this stage, I've got 4 intermediate wires left. So I've divided from 16 candidates down to 8, from 8 candidates down to 4, and so on. So I'm going to need 4 stages of this. Okay, from 4 down to 2, from 2 down to 1. And then at the very end, I need the same thing I always need. I need an inverter. And I need this keeper or pull-up transistor. Okay, and there's a whole bunch of stuff down below that I haven't shown. Right? I just have to repeat this multiple times, but it'll take me forever to draw that. Does everybody get the structure? So it's like a logarithmic tree. I'll let you stare at it for a second. I'm going to look and see if I see comprehension or if I see confusion or anger. If it's anger, that's not good. So, so what do you think? You get how this works? All right, see some nodding, so I'm going to take that as yes. So let's count what the area of this is. So we want to remember that 147. Okay, that's the number to beat. So let's see if I can erase something here. Maybe this can go up. Okay, so number of transistors. So how many SRAM cells do I need for some number of inputs? This one was 16 inputs. But in general, how many SRAM cells do I need? Yeah, so I need log 2 of the number of inputs. Okay, and then I'm going to need, I already showed up somewhere. I guess I've hidden it, but I need 6 transistors per SRAM cell. Okay, and then I need these pass gates. How many pass gates in this whole structure? So the first stage would be 16, or the number of inputs. Second stage would be half that. Third stage would be a quarter of that, and so on. So it's a geometric series. So what's the sum of that geometric series? So I wrote it down, so if there's no volunteers of what the sum of that geometric series is. The sum of that geometric series is basically 2 times the number of inputs. I mean, the number of inputs would be like 2 to the k, if we say this is a k-level MUX, but that's also just the number of inputs, minus 2. Okay, so sum of the geometric series would be 2 times the number of inputs minus 1. If you go add up that geometric series, we could take one more pass gate away because the last If I just add up the geometric series, I also get a final one pass gate that's always on, which is not useful, so we just remove that. So we get number of inputs, 2 times the number of inputs minus 2. Okay, and that's the pass transistors. Okay, so this is pass transistors, this was SRAM. And then I have this output structure, which is just 3 transistors at the end, same as always. Okay, so hopefully everybody's with me. If I do the same thing I did before, so if I say, okay, let's plug in inputs equals 16, and let's say the drive of the pass transistors, we increase it to 5 times the minimum, so we're going to upsize our pass gates. We plug in our simple area formula for a transistor as we upsize it, and if we do that, we get an area of 123 of these minimum width transistor areas. So it's a reasonable savings. We went from 147 down to 123. So we save maybe, I don't know, 15 or 20% of the area. What do you think we did to speed? Is this going to be better or worse for speed than the one level structure we had at first? Yeah, it's going to be worse. So it's going to be worse because, again, to first order, when you're optimizing transistor circuits, you can just think of them as if they're resistors, because they are actually nonlinear resistors. So they, within their main operating region, they do actually behave like a resistor once you turn them on. So putting multiple resistors in series, and then you've got some capacitance that they have to just charge at the output, is going to be slower than just having one transistor or resistor discharging that capacitance. So the switching speed is lower, so there's a trade-off here. Speed is slower. Okay. Yeah, let's see, move this up here a bit. Okay, so we can also do intermediate solutions, and you already hit on this. So, which is, we could do a 2-level mux. Okay, so that was for 16 inputs, that was a 4-level mux, smaller but slower than the 1-level mux. We can actually do in between points. So a 2-level mux is a good idea, and let's follow up on that proposal. So 2-level mux. So 2-level mux is basically made by, for this one, 16 inputs, we're going to cascade 4-to-1 mux, and then another 4-to-1 mux. Okay, so if we had 4 4-to-1 muxes, and then they produce a 4-bit output, we can put that into another 4-to-1 mux, and we get our 16-to-1 mux function. That doesn't gain us anything unless we apply a trick. The trick is we have to share the SRAM cells across all the first-level muxes. See if I can, this is like my most complicated figure. Just figuring out if I have enough room on this or I need a full board. I think I better get a full one. Let's see. Let's see. Okay, so I've got four inputs here going into four pass transistors, and I'm actually going to control all of them with the same SRAM cell. Okay, so all of those are going to go on as a unit. And they're each going to have basically an output wire. Okay, so that doesn't look super useful. I mean, I turn this on and I copy four inputs onto four outputs. But I'm going to repeat that structure 4 times. So I'll show the bottom of that structure. Okay, so here's input 14. Here's input 15. Okay, so this SRAM cell actually also controls 4 pass gates. I'm only showing the last 2. And so I repeat this whole structure 4 times. 4 groups of 4 pass transistors, each controlled by 1 SRAM cell. So if I turn on this SRAM cell, these 4 inputs get copied onto these output wires. If I turn on this bottom SRAM cell, the last 4 inputs, so input 12, 13, 14, 15, get copied onto these 4 wires, and so on. Okay, so depending on what I set, I copy a group of 4 signals onto this 4 intermediate values. Okay, and this goes into my second stage 4-to-1 mux, which now has separate SRAM cells for everybody. This one, and this one. Okay, so this is my second 4-to-1 mux, which is a regular 1-level pass transistor mux, right? I turn on exactly one of these signals. It's going to pull one of these 4 intermediate signals out to the output, and then I have my standard, inverter to make sure I isolate downstream capacitance, and this weak pull-up to make sure I pass a logic 1 properly. Okay, so everybody understand how it works? So it's leveraging the fact, like by programming this, what the CAD tool does is if I want any one of these 4 routing wires to make it to the output, that's what the CAD tool says I should connect, then it'll program a 1 in here and the other 3 SRAM cells will have zeros. That actually copies 4 signal paths are activated. So I get 4 signals making it to the second level. And then the CAD tool programs one of these 4 with a 1 and the others with 0 to make sure it gets the right value to the output. So we're essentially saving SRAM by exploiting the fact that we don't really care. Like it's okay for us to select more values to go onto these intermediate signals. Okay, so that's what we're doing. And then we'll basically just pick the one we want later. Does that make sense? Yeah. This doesn't put any additional restrictions on the CAD tool. So the router basically is still only, so inside the router, like the router that's inside Quartus. So Quartus has a router that eventually wires together your design. It's not actually told how these muxes are built, okay? It's just told, essentially it's represented as a graph, okay? So all these routing wires would be nodes. This input pin of a lookup table would be a node, and it would have edges for the fact that all 16 of these are legal to connect to this. So the router doesn't care, right? Because it actually can connect any one of these 16 inputs to the lookup table input, no matter how I build this mux. After the router is done, a final tool called the assembler or programmer basically looks at what did the placement do, what did the routing do, etc., and it basically works out all the ones and zeros. So that tool has to understand how the mux is built. So the programmer would say, okay, you want to go from input 0 to this LUT input. I need to put a 1 here and a 0 in these 3, and I need to put a 1 there. But that's the only part of the flow that needs to know how the mux was built. Does that make sense? I guess the other thing that needs to know is the detailed delay models that go into the timing analyzer. Okay, so how the mux was built has some impact on timing, and that has to be told to, that detailed delay extractor. But the optimization algorithms like the router don't actually need to know. This doesn't imply any additional restriction. Does that make sense? I mean, if you actually started programming a bunch of ones and stuff, okay, then you could actually blow up the chip. And people actually have done things like that, like saying, can I make destructive bit streams that can melt in Amazon? Amazon will actually rent you FPGAs in your cloud. So as soon as they do that, what do a bunch of people do? They try to figure out, could I actually destroy that hardware? And given an arbitrary bit stream, like if you actually were allowed to send an arbitrary programming file to the FPGA, yes, you could melt it. So Amazon actually has a tool that verifies the bit stream. Like it goes in, it checks. Did you just short power to ground like 1,000,000 times, etc. So it checks for various things that it knows would be damaging. You could probably beat it. Like it's actually always hard to be checking for everything versus the person who's trying to come up with new ways to get past the checks. I'm not sure if that's a socially productive thing to do, but if you're interested, you could probably do that. If it's your own FPGA in your own lab, then you could for sure do this, but your advisor is going to be really annoyed with you. So, okay, so let's see how well this one works. Okay, so the number of transistors is equal to, okay, SRAM cells. How many SRAM cells do we need in this for a 16-input mux? It's like a test to see if you're following me. So how many SRAM cells in total in this? So I drew 4 here, so it's at least 4. So how many are in this stage? 4, right. So there's 4 in this stage, 4 in that stage, so it's 4 plus 4. Okay, it'll be slightly different numbers for different numbers of inputs, but for 16, that's the right answer. So that's your SRAM. Okay, then pass transistors. So you just add up how many in the first stage, how many in the second stage. First stage is actually always easy. So how many in the first stage for 16 inputs? It's just 16, right? So you need 1 per input in the first stage, plus 16, and the number in the second stage you can see right here, right? It's a 4-to-1 mux. So 16 plus 4. Okay, so that's pass transistors. And then we always have our usual output restoring circuitry, so 3 more. If I make these pass transistors 5 times the minimum drive strength like I did before, I use my simple area model for transistors, I plug all the numbers in, I will get the area of this is equal to 111 of these minimum width transistor areas. So let's see. That compares to 147 when we did the fully encoded one, and let's see, where's the number for the other one? Well, I guess and it was 123. So this is actually the smallest one. Okay, so this is smaller than 1 level. It's also smaller than K level, so it's a good trade-off. What do you think its speed is? Do you think it's, compared to those other 2 designs, 1 level or K level, how do you think the speed of this will compare? Think it's closer to the speed of the single level? Yeah. Yeah, that's a good answer. So the speed of this is a little slower than single level, but not too much. It's because it's only, it's 2 pass gates discharging this capacitance instead of 1 in series. So it is a little slower, but it's significantly faster than the K level one. So it's a pretty good trade-off. Yeah, so that basically is where that one stands. So it's the smallest. It's also pretty fast. And we use routing muxes like this all over an FPGA, so that's why it's useful to think about how do you build this. This is kind of the dominant design. So for really small muxes, like 4-to-1 and so on, 1 level mux makes sense. As you get into bigger muxes, usually 2-level is the best. Okay, so the other thing we need to look at let me erase some of this. Okay, so we've done kind of 2 of the 3 area components of our FPGA. Yeah. Yeah. You mean this? Do we need that? Yeah, I do have the 3 here, but I just wrote on the next line. So, sorry, it's here. I can write it here as well. Maybe I should have written it there too. Yeah, it does still need that 3. Okay, so we've done 2 of the 3 components of our kind of simple logic-only FPGA. But the last component is the general routing area. Okay, what do I mean by that? Well, so far I've built the LUT and I've built the muxes to connect the LUT inputs to the routing wires going by it. But I haven't built the routing wires or any switching between the routing wires. So, or the ability to actually go from the output of the LUT to the routing wires. Is it everything okay? Oh, could you build a decoder? Yeah, you could build a decoder as well. So you're saying like use a smaller number of SRAM cells and then build a decoder. You could do that. I haven't actually seen that done. I don't think it's any bigger, or I mean any smaller than just storing all the SRAM. Let's see, could you build 2? But you could do that. And maybe for decoding pairs of SRAM, it might work well. So that's a good question. There are low-level tricks that people come up with for these circuits that are generally useful. So I haven't seen that one used, but that's a good idea to try. Okay, so we need to estimate the area of the general routing. Okay, all the routing wires, the switches between those wires, etc. Okay, so how do we estimate this? So the best thing to do would be to use a full CAD flow, right? Figure out how many routing wires we need per channel to route, most of a bunch of designs or maybe all of them. We're not going to do that. I'm not going to write a CAD tool on the blackboard. So what we're going to do is we're going to use a simple model. To gain intuition. Because the other, one downside of running a CAD tool is you got to go write it. But the other one is if you don't have some intuition, well, it's bad. You kind of just trust whatever the CAD tools tells you, even if you've set it up improperly and it's not making any sense. So you want to have an intuitive sense of what should be happening. Okay, so an equation that helps us with that is this one. Okay, so W average, this is the average channel width that I need. It's the average number of wires per routing channel that I'm going to use, is equal to lambda, and I have to define these. So lambda is the number of used inputs and it's an average per block. Okay, so we're using a 4-input lookup table. So this lambda is number of used input per block, which for us is a 4-input lookup table. So what do you think lambda is going to be? Maybe you don't know the exact number. You might be able to give me a range. So any guesses? Number of used inputs per block, and our logic block is just a 4-input lookup table. So you might be going, this sounds like a really easy question. Maybe it's a trap. It's not really a trap. So if you go, that sounds obvious, go for it. So you think 4? Yeah, so it's not going to be more than 4, okay? You will wind up with, synthesis tools can't always use all the inputs on a lookup table. So for sure, it won't be any more than 4. In practice, it'll be a little bit less. Why is it a little bit less? Maybe I've got a bunch of flip-flops before some AND gates. And the tool, when it goes to figure out how to put this in 4 LUTs, it just finds I just can't find 4 inputs worth of work between these flip-flops. I only found 3 inputs worth of work. So this lookup table is only going to use 3 of its inputs. Does that make sense? So it depends on the exact structure of your circuit and the exact structure of your circuit and how good your synthesis tool is. But a good estimate would be, lambda for a 4 LUT, probably about 3.5. Okay? So I'm going to use that. So close to 4, but not perfect, because there's parts where you can't use the LUT to its full potential. Okay, so what are the other things here? R bar. R bar is like the average distance you need to go from the source of a signal to its destination, which is going to impact how much wiring we need, right? If we have to go a long way for every single signal, well, we need more wiring. If we have to go a short way, we don't need as much wiring. So R bar is the average distance from the source of a signal, or the output of the block, to the input that's receiving it. Okay, so maybe I should write that as source and sink. Okay, this is output of a block is like the start of a connection. Input of the block it gets to is the end of the connection. Okay, and then the divide by 2 comes from 2 dimensions. Why do we divide by 2 for 2 dimensions? Basically, half our wiring is going to go vertically and half's going to go horizontally. So when we're trying to figure out how many wires do we need per channel, this equation is essentially lambda times R bar is going, how much wiring do we get going past a block? And then the divide by 2 says, well, half is vertical, half is horizontal. So your routing channels only have to provide half that many wires. Okay, so let me draw you a picture. Maybe make this R bar part a little more clear. So let me show you what I mean by this R bar equals 4. Yeah, maybe I'll erase the last one. It's probably confusing. Okay, so this is my output here. It's saying, well, I normally go, maybe I will draw the last one. I go 4 units over before I get to my destination. So that's what R bar equals 4 means. If R bar was 2, then I would just go a shorter distance, like that, and into my destination, on average. You're not saying this happens for every connection. Some are going to be shorter, some are going to be longer. We're saying the average connection, if R bar was 4, so that's what I'm drawing here, I go 4 units over before I go into my destination. Okay? And R bar equals 4 is actually a reasonable estimate. So it turns out for a lot of FPGA architectures that that's a pretty reasonable estimate of how far you go. I don't entirely know why. Just like there's enough locality in circuits that CAD tools can place things pretty close, but the average connection you can't place right beside it. It's not that local. So this turns out to be a pretty reasonable number, even though it's going to vary some from circuit to circuit. Okay, so this WAV is basically coming from if I have let's say I have 3.5 signals that need to come in here. Let's just round that off to 4 because it's easy to draw. And R bar equals 4. Then I would need to have 4 signals all running in parallel to get here. And then I need to repeat that for every single overlapping block. So this block would come out and it would drive 4 signals over. And this block would do the same, and this block would do the same. So if R bar was 4 and lambda was 4, I would need 16 wires. That's like my steady state number of wires. Now I've drawn a one-dimensional FPGA where all the wiring goes horizontally. If I drew a two-dimensional and I say half my signals are going horizontally, so half are going vertically, that's where I get to divide by 2. Does that make sense? Okay, so I kind of drew 2 of these. You can visualize if I drew the next one, it would be here. And if I drew this last one, it would be 4 more wires here. Okay, and then when I got to this guy, its wires wouldn't overlap. It could use these routing channels. So that's why you get this kind of repeating pattern. If the average distance I go is 4 and the number of signals I need to take over was 4, then I would get in a one-dimensional FPGA that my average number of signals passing by a block is 16. But in a 2D FPGA, if I just split this in half, I say half of the wires going this way, half's going that way, I would get 8 wires per vertical and 8 wires per horizontal channel. Does that make sense? Okay, so that's where this equation comes from. And I've kind of told you the reasonable numbers to plug in. 3.5 for lambda, 4 for R bar. Okay, so this gives me like the average number of wires that I have passing by some block or in some routing channel. Do you think I can use all the wires in a routing channel kind of repeatedly across a whole FPGA and it's going to be okay? What do you think the odds are of routing completion if I did that? So I built exactly 16 wires in a routing channel, and then throughout my average part of my design, I'm actually using 16 wires in a routing channel. Do you think the CAD tool will like it or not like it? So the CAD tool will never complete that, okay? Because the switch patterns, we have kind of limited switching between wires, right? We're not connecting every wire to every other wire with full crossbars. Remember back when we looked at our various styles of logic element and switch network scalable, we said full crossbars aren't scalable. You just can't connect everything to everything, and as your crossbars get big, that gets really inefficient. So FPGAs, they use smaller muxes. There are a whole bunch of limitations on which routing wires can connect to each other. So you can't actually use all the routing wires in a channel. It's certainly not very often, right? So if you did that once in your chip, maybe it would work. If you did it in every single location, like the 10,000 locations in your chip where you have routing channels beside blocks, there's no chance it's going to work. So this gave us the average routing channel. We actually need to find essentially the peak, okay? That's what we really need to build. We need to build a routing channel that has some extra margin. So let me erase this and write that down. If I have any of these available. Nope. Okay. Okay, so we can't use all the wires in a channel. Okay, so it's because the switch pattern is sparse. Okay, so we need W peak not W average. So I guess there's like 2 reasons that, yeah, we need to find, there's going to be some variation in routing demand across the circuit. So we want to find the peak because that's going to cause us the most problems. Part of the job of a routing CAD tool is to actually spread out wiring. So the routing CAD tool inside Cordis or Vivado is actually trying to reduce this peak, if it can, by spreading things out, but there still will be a peak. Maybe more than one in the chip. It's going to be the parts of the chip that, part of the design that has the worst locality, et cetera, the most congestion. So we need to deal with that. And then we also need to deal with the fact the switch pattern is sparse. So some wires, even if we perfectly spread out demand, we can't actually use all the wires because some of them are just going to be blocked by, we don't have the switches to get to them. You know, if we use this wire and this wire, this other wire is not usable. How much should we add? This is hard to know without running a bunch of CAD tools, but a reasonable amount would be add 50% to 100% extra width. Okay, so if we use this equation, we're going to get a W-av. We shouldn't use that W-av as the number of wires we put in our channel. We should multiply it by, I don't know, between 1.5 and 2x. If we're making a routing architecture with lots of switches, then we could probably get away with 1.5 because we won't have as much kind of blocking. If we're making an architecture with fewer switches, and that's not unreasonable because it could save us area, but we're going to pay for that by we're going to have wider routing channels. So now we'd have to probably multiply by about 2x. So we're just going to split the difference. We'll use 70%. Okay, so we'll get that W-av and we'll multiply it by 1.7. Okay, so let's say now I want to put in, okay, so the channel width that I need in my chip is equal to lambda r bar over 2, right? I already had that, times 1 plus this guard band. Right, this factor to account for peak effects and limited switch flexibility. Okay, if I plug in the numbers I already gave you, said lambda, it's for sure no bigger than 4, but more likely it's about 3.5 for a 4-let. R bar, you have to run CAD tools to measure this, but I know it's typically about 4. Divide by 2 for the 2 dimensions. And then 1 plus, we chose a guard band of 0.7, which is reasonable. If we do all this, we get 12 wires per channel. Okay, so without running a CAD tool or anything, we've come up with an estimate of how many wires we need to put in every single channel of our FPGA. Do you know how many wires per channel there are in, let's see, you were using ARIA 10, okay? So how many wires per channel roughly does ARIA 10 have? Is it about 12? Does that sound reasonable, or does anybody have any idea? You may not know. You may be like, I don't know, Quartus just does stuff. If you actually looked at the routing, you might have a sense of how wide the routing channels are. So ARIA 10's routing channels are a lot wider, okay? So they're on the order of, I have to go look up the exact number, but more like 300, okay? So why is, okay, if this 12 has any validity, why would ARIA 10 have 300? What do you think? There's one dominant factor, okay? So, you know, there's all sorts of details about, you know, I just said 70% guard band. They're going to be more precise. They'll have measured like how much blocking they get with CAD tools and so on. But there's one big factor that does account for this. So my logic block here, our logic block, is a 4-let. So very small. Lambda is quite small. What's the logic block in ARIA 10? Maybe you don't know this yet because we haven't gotten to it yet. But so ARIA 10 has 10 adaptive logic modules. If you read the Stratix 10 paper, you'll see that an adaptive logic module can do several things, but one of the things it can do is 2 4-lets. So it's worth at least as much as 2 4-lets, and there are 10 of them. Okay, so that's 20 times as much stuff that they put in their logic block, and like 20 times the expected number of inputs, or in that ballpark. If I multiply this by 20, I get up to like 240. Okay, so it's much more in the ballpark now. Does that make sense? ARIA 10 also has a lot of longer wires for speed. Longer wires do cause more blocking. Like you tend to waste some of your wiring when you have longer wires. You don't always use the whole thing. So the main difference is this lambda is hugely different for an architecture like Versal or ARIA 10. It's much bigger, and that's why this is a much narrower channel. But it's also why these equations are quite useful, because I know this equation, even though this is hugely different than that commercial architecture, I know it still makes sense. And people do make FPGAs with really small logic blocks, and when they do that, they should make their routing channels a lot smaller. Okay. So let's see. Let me erase one more of these. Okay, so that was all to figure out the number of tracks per channel, which is, yeah, actually kind of hard to figure out with a CAD tool. But this is a pretty reasonable estimate. Okay, so now we're going to assume a really simple routing architecture. Okay, so we're going to make all wires length 1. So they only go past one logic block before they end. We're going to use mux-based switches. And we're going to make the muxes pretty small. We're going to make them 4 to 1. Okay, so see when we get to routing architecture, mux-based switches are dominant. That's the most common type. And we can make this work with 4 to 1 muxes. You could also make your muxes somewhat bigger. Both are reasonable, but this is a reasonable choice. Okay, so what does this look like? We've got a lookup table. This will be a channel width of 2, so we're really doing 12. And every single one of these wires is going to have a mux in front of it. And the mux, it's going to be built like one of the muxes that it's going to be built as a 1-level mux because it's very small. So for a mux this small, a 1-level mux actually works very well. We don't need to go to 2-level muxes. And it's going to have, an inverter on the output because that's what we've been putting there to isolate the capacitance. This routing wire, even though it only spans 1 logic block, is still a fair amount of capacitance. So that inverter is our friend to isolate that. With 4 inputs, we can take basically 1 signal from above. We can take 1 wire from below. We can take 1 wire from the left. And we can take an output. Let's say we've got an output here. Okay. And that's enough. So we have connectivity from a logic block to our routing. We can go in each direction. So this wire is going to the right. Could be continuing a route that came from its left or above or below. This wire, we'd make the mux go the other way. Okay, so maybe this mux goes, or maybe I'll do this wire. This wire, the mux would be letting you go the other way. Okay, so its inputs would be coming from this side and from a different logic block over here. And if I repeat this, this is basically a routable routing architecture. You need at least this much, like the ability to keep going the same direction, make a turn from above, make a turn from below, and get on from a logic block. So you need at least that. If I have that much, I can make this thing route. And if I want to get more detailed about, well, what if I had a few more switches? So I shouldn't take any switches away. Taking any switches away makes this really hard to route. Adding a few might be okay as well, but this will work fine. You kind of have to take my word for that, I guess, but it's a bit intuitive. I have I have some routing choices in every direction. Okay, so I want to work out the area of this. So the area of this mux, so it's a 4 to 1 mux. I'm going to build it with a 1 level, because for such a small mux, that's good. So I need 6 transistors per SRAM. How many SRAMs do I need for a 4 to 1 mux? I'm building it with a 1 level mux. So with a 2 level mux, I'd need 2. But I'm just going to build it with a 1 level mux. So I need 4, right? So I'm going to use 4 SRAM cells. Okay, then the number, it's a 1 level mux, so how many pass transistors? 4, right? So 4 pass transistors. And I'm going to, again, make those a bit bigger. So their area is going to be, I'm going to give them 5 times the drive strength, just like I've been doing all along. But that gives them an area of basically using my little area equation, 0.5 plus 2.5, or 3 times the area. And then I always have this plus 3 for the inverter and the level restorer. Okay, so if I add all that up, I get 39 minimum width transistor areas. So this mux isn't too big, but I get a whole bunch of them. So I need to take the repeated layout patterns. Basically, I need to get all the muxes that are driving this horizontal piece of channel or this vertical piece of channel. Because if I repeat that over and over again, I will get a full array of LUTs surrounded on all sides by routing channels. So I need to figure out how many muxes I have here. Whoops. Let's see. Okay, so the area of these routing drivers is equal to, okay, so what is this, in this tile, so this piece of horizontal channel, this piece of vertical routing channel, how many of these muxes do I need? How many of these routing drivers? You just walk me through the equation, right? You don't have to like do the calculation in your head. So you're going to need W, right? We calculated how wide was our channel, and we said that it should be 12. Okay, so we're going to need to know that. We need to know the area of one of these muxes. We just figured that out. Okay, but how many of these muxes are there? And all these wires are length 1. Okay, so they only go 1 unit and then they end. So within this tile, each of these wires is going to have a driver, because otherwise they don't go anywhere, right? If I had longer wires, then some of them wouldn't have a driver within this one tile, but I don't. They're all just 1 length. So given those hints, how many of these muxes do we have in this kind of repeated layout unit?
2W?
Yeah, so we just have 2 W's. So W in the horizontal direction, W in the vertical direction, okay? So that 2 comes from horizontal or vertical. And then we just need to multiply by the area of the mux. Okay. And if I plug those numbers in, so we worked out that W is 12, and the area of this is 39 of these minimum width transistors, which means the area of this is 936 of these minimum width transistor areas. Okay, so it's actually pretty big, right? So this routing area adds up pretty quickly. These muxes give us 2 things: the ability to switch from one wire to another, and also the ability to connect outputs into the routing. So we're done now, right? We can do logic in our LUT. We can connect it to our routing. The routing wires can connect to each other, and then those input muxes allow us to get back into the block. So that's all we need. We can now do arbitrary logic. So we just need to add up the area of a tile. Okay, so again, the tile is like this repeated unit: LUT plus the routing above it, and the routing below it, and the routing to its right. Okay, so we got the area of the LUT. We've got 4 inputs. Every input has an input port, or mux. Okay, so 4 areas of the input ports, plus the area of the routing drivers. Okay, so the LUT we said was 217. Our best way of building, most area efficient way of building these input ports when they're 16:1 muxes was 111. Just worked out the area of all the routing drivers is 936. If we add it all up, we get 1597. Okay, so this is like minimum transistor areas, but clearly that's a reasonably big number compared to just a gate. Now a LUT can implement several gates worth of logic usually. Just putting a single NAND gate in it, NAND 2 gate would be underutilizing it. So it can usually do several, maybe as many as 5 or 6, or but that's probably about what the most you would get on average. So this is quite a bit of area compared to a gate. So it's showing us part of why is programmable logic less efficient. The more important thing I want to get out here, though, is if I take the routing area, which is this part, these two components together, that routing area is 86% of our total. Okay, 86% of our total transistors. We're not talking about the wires. We're assuming we're transistor dominated, and we spent most of our transistors on the programmable routing. So we can't neglect that. So when we're doing FPGA architecture studies, we always have to be thinking about the routing area. And it is a mistake that many people have made. Because it's easier to think about the logic blocks and other function blocks, so they don't really want to think about this as much because it's harder to estimate channel widths and so on. But it's not like a second order effect. It's actually the first order effect. So you have to consider it. Now we did a pretty simple architecture here. Small lookup tables, short wires. You can optimize your routing architecture and your logic block architecture better than this. So you can and people do make FPGAs with less than 86% routing area, but you're still going to wind up at least 50%. Okay, so a really optimized FPGA, usually they're in the range of 50 to 70% routing area. So lower than this, but still very important. Okay, so any questions on any of that? Okay, if not, we'll take a break till 5:38. Okay, and then we'll go on to actually looking at some results for logic block that come from published papers and CAD tools and so on. But hopefully this analysis has given you some intuition of how do you do these studies and what's inside. Okay, so let's meet back in 10 minutes. how you can model its area. Now we're going to go through some research results on how you make good logic blocks. Then we'll go through other function blocks like RAM blocks and DSP blocks, and then eventually into the programmable routing. So not all today though. Okay, so logic blocks. So the dominant logic block is, we kind of talked about this when we were talking about architecture style, is something often called a logic cluster. So it uses a k input lookup table. So here I'm showing a 4 input lookup table. That's combined with at least one flip-flop so that we can also do sequential circuitry. So here I'm showing you can either take the registered or the combinational signal out. Some FPGAs, most commercial FPGAs will let you take both out. So you can take out both the combinational and the registered signal. But this is the dominant style of logic element, a lookup table plus a flip-flop. And we'll look at a few variants on that. But what we just did here was a very fine-grained logic block, a single lookup table. So the dominant logic block is bigger than that. It's a logic cluster, which means we take n of these basic logic elements and we combine them into a logic block with some local routing. Okay, so that local routing could be a full crossbar as long as your cluster's not too big. More commonly, it's a somewhat depopulated switch network. So it's not quite as flexible as a full crossbar, but it's usually pretty flexible. Okay? We usually don't bring, okay, so if you counted all the inputs to the lookup tables, if I have n of these lookup tables, or BLEs, and each of them has k inputs, then I need k times n inputs from the regular routing, the island-style routing in between these things. When I build these logic clusters, I don't normally bring all of those in. I bring in some smaller number I, so I don't need quite as many routing ports or muxes to the general routing. And then I'm showing here that we're just bringing in one clock. Okay. Okay, so we kind of have covered some of this, so this is a review. So the dominant kind of logic element used in commercial FPGAs is LUT-based. Why? Well, I guess maybe I'll just ask this to see if people remember. Why is LUT-based good? What are some strengths of a lookup table? Yeah. Yeah, so it can do any function. So so that basically means it gets lots of functionality for a small number of routing ports. And routing ports, as you just saw, are expensive. So we did a 16-to-1 mux. They're usually 16-to-1, sometimes even more than that. So that's a pretty expensive thing. So if your connectivity to the routing is so expensive, you'd like your logic element, once you get signals there, a LUT can do anything you want with them. So that's good. It's also an efficient synthesis target. So you have to write CAD tools for this. And describing what can go in a LUT is pretty easy for a synthesis tool. Count the inputs. That makes your synthesis tool, that can help you write more complicated algorithms and still get them to work. And that can get more out of your chip. Okay, so that's why people have kind of gravitated towards lookup tables over the years. But there's a question of what's the best LUT size. And we usually use the variable k to represent how many inputs go into a LUT. So I'm not going to answer that right now. We're going to look at a paper that set out to answer that. Okay, so the other architecture questions, I just said that typically people don't use lookup tables alone as their logic block. They group them into a bigger thing called a logic block or logic cluster. This gives us that 2-level hierarchy that we talked about earlier. So we're clustering to a bigger block that can help make our CAD tools faster because the placement problem is smaller. And we already talked about this as well, but it allows some word-wide signals. So clock enable, asynchronous clear, synchronous clear, etc. of our registers. We don't need the same granularity of we need to bring in a different signal for the clock of every single register. We can now bring in one clock and it just broadcasts to all the registers. That is a restriction on the CAD tools, but it turns out designs, that's the way people make designs, it works well. They use the clocks across a lot of registers. It's a little bit less true for clock enable. Well, they'll use it across some registers, but not thousands, but they will use it across usually all the registers in a word. So a logic cluster gives us a kind of a natural way to say, well, if people usually use this signal to drive a whole bunch of flip-flops, then I'll just bring in one or two of that and connect it to all the flip-flops. So it's kind of a natural way to enforce some signal sharing, and that saves you area. If I bring in if I have 10 flip-flops in my logic block, but I don't bring in 10 clock enables, I bring in 1, I just saved 9 routing ports, and that saved me a bunch of area. So if that's not that much of a restriction on the CAD tools, that's a good thing to have. Questions on this, though, are what's the best size? So N, how many of these basic logic elements, which are lookup table plus flip-flops, should we put in? And how many inputs should we bring in? So should we bring in all k times n inputs we could ever want, or is less a good idea? And then how much interconnect should we put in the cluster? So we could put a full crossbar in for our local interconnect, but maybe that's overkill. Okay, so how do we answer this? So you basically have to answer this empirically. We could have intuition with simpler models, but once we get into the trade-offs of this, you can't really do it without writing CAD tools. So we need to have some kind of compiler or CAD tool that maps circuits. So we go collect benchmark circuits, or we make benchmark circuits, and we're going to map them to our proposed architecture. And usually we have a bunch of architectures that we're having compete against each other. So we map a bunch of circuits into each of our candidate architectures. We estimate the area and delay that we achieve on average across those benchmarks for each one of those architectures, and we pick the best one. Okay, so at the end of this, we know the efficiency of the architecture, and we pick it. Okay, so here's a possible CAD flow. First I have to collect benchmark circuits. This is actually a lot of work. So there's some academic CAD benchmark suites that have been collected that you can use. Companies jealous, they collect these. So when I was at Altera, everybody who sent a bug in, so every time Quartus crashed, we'd ask, oh, could we have your design, and we'll debug it. And if they didn't forbid us, we would just include it in our benchmark suite if we thought it was a good design. So we had a way, the less stable our CAD tools were, the more benchmark suites we were exposed to, although it did help us make our CAD tools more stable over the long run. And companies like Altera and Intel and Xilinx really guard these benchmark suites. So first there's customer information in them, so you can't let them out, but they're also important for designing their next architecture, so they would never want to share them. So there's significant effort and IP in getting these benchmark circuits. Okay, so I got to take those, I put them into a CAD flow. So here's my first proposed CAD flow. So these benchmark circuits are in, let's say, Verilog. So the first stage of logic synthesis is something called extraction. Extraction is basically a whole bunch of, or elaboration. It's basically a whole bunch of template matching, right? When you write this always block, that means a flip-flop. When you write this, that means a mux, etc. So we recognize what is this and put it into a net list, so it's a data structure. That's not a lot of optimization in that. It's just like figuring out what do you mean with this Verilog. Then optimization, you go into the first optimization, it's optimize the gates. So you basically turn all of that into logic equations and you start simplifying them using a bunch of algorithms that are kind of like the Carnot maps you learned in second year, but applied on things with maybe millions of variables automatically. So you try to reduce the gates, you get rid of unnecessary ands, etc. Now we don't really have gates on an FPGA, so then you have a step called technology mapping. So technology mapping basically would say, okay, you've got gates and flip-flops, so I'm going to leave the flip-flops alone, they're okay. But all the gates I've now got to map to lookup tables. So this is done with various algorithms, but they're kind of like bin packing. You're sticking gates into these lookup tables until you run out of inputs. And then you got to make another lookup table. And you try to minimize the number of lookup tables, and you try to minimize the number of lookup tables in series, because that's going to affect your speed. If you have a whole bunch of lookup tables in series, then your signal's got to go farther to be slower. Okay, so that's what your synthesis tool is going to do. And it's a lot of work, actually, to write these tools. So I'm tired after writing those tools or getting those tools set up. So now I'd like to evaluate my architecture. So I'm going to say the area is the area of a LUT. I know how to estimate that. I'm going to do my transistor level design like we just did. And the number of LUTs. And I got the number of LUTs because that comes out of the synthesis tool. And then my delay, well, I've got the delay of 1 LUT. I'll get that by doing my transistor level design and spicing it. And then I'll take the depth. So that's the number of lookup tables in series the most number of lookup tables that are in series in my design. So maybe in this case, the most lookup tables in series between flip-flops is 2. That would mean my depth equals 2. Okay? So I can get the depth and I can get the number of LUTs after synthesis, right? I don't need to go through placement and routing. So I don't have to write those tools. I can get the area of a LUT from my transistor level design and my area models. I get the delay of the LUT from the transistor level design in SPICE. What do you think? What do you think of my architecture flow? So if I do this, and I go publish some results on it, you're a reviewer on this, what do you think of this paper? Sorry? Yeah, it's missing the routing. Okay, so is that like a small error, or is like a nitpick, like I kind of feel bad bringing this up, but you forgot the routing, or is that like a red flag? Yeah, so this, and there are actually probably not that many anymore, but there were actually quite a few papers published like this, and people still do it sometimes, because it is a lot of work to get a CAD flow going, so it's very tempting to say, I've made a new logic block, and I just want to go this far and evaluate it. But the problem with this is, yeah, the routing doesn't show up here anywhere. So, you can't do that, okay? So even if this is the most CAD flow that you can bring yourself to write, you still want to model the routing explicitly. So what you could do that's a bit better is, okay, the area, we got the number of lookup tables. We shouldn't just say what's the area of a lookup table. We should also include the area of its input ports. So we know it's got k inputs, and we need the area of its input ports, so we could do what we just did. And we need to estimate the area of the output ports. What we just did, the output port is kind of mixed in with the routing muxes. And the delay, well, we don't know exactly what the delay of the routing is, but we can at least put some constant in that is probably bigger than the delay of a LUT. So we take the delay of a LUT, and we'll assume some routing delay and multiply that by depth. So this isn't any more CAD tool development, but it is a better model. So definitely better. What do you think of this, though? Would you still have any concerns about this? There are weaknesses to this still. So it's better, they've taken a better shot at it. What are the weaknesses of this model? What are the difficult things to estimate? Yeah. Yeah, that's true, actually. I didn't. So let's say the switch block is in this output. So that's a good point. So let's say I put the whole switch block in that area of the output port. But I guess you're highlighting an important thing. That's difficult to do, right? The reality is that's a function of channel width and all sorts of stuff. So I can say I included it, but I mean, I just picked a number. So I'll say my number includes it, but you probably don't have a lot of faith in that because I just guessed it. So yeah, there's a lot of, my routing model isn't really going to adapt to, as I change the size of the lookup table, for example. Let's say that's what I'm doing. Maybe it's changing how local my routing is. And therefore, the width of my channels has to change in an unexpected way. I'm not going to capture that, right? Same thing for the delay of the routing. So I put some number in for the delay of the routing. Like, if I'm changing the lookup table size, for example, am I going to assume that delay of the routing is constant? Am I going to assume it's changing somehow because maybe things are getting spread out or wires are getting physically longer? I don't know, right? Without doing a whole bunch more modeling, I just don't quite know what to put in there. So it's better, but I'm going to have some difficulty basically justifying these, right? Because I'm going to have to do a lot of guessing. Okay, so now this is, what do you do then? Well, you can build a full CAD flow. So what I was showing you before basically ended after synthesis. Synthesis makes a net list of lookup tables and flip-flops and maybe RAM blocks, et cetera, that exist on your chip. But there's a whole bunch of things after that to finish your design. So this is a popular CAD flow for evaluating architectures. So it's called the VTR or VPR. It kind of goes by two names somewhat, architecture evaluation flow. So it starts out with benchmark circuits. It actually has a few different synthesis front ends. Okay, so Odin 2 is one of them. That does what I just said, elaboration. What does your Verilog mean? Turn this into gates and flip-flops. There's a tool from Berkeley called ABC that does the logic optimization and technology mapping to lookup tables. Things like RAM blocks and DSP blocks basically just pass through this part. Like the elaboration recognizes that's a RAM, that's a multiplier, and they aren't really optimized by this stage. They just go through it. Okay, after that, we pack into logic blocks. So we have a logic blocks more than just a single lookup table. It has some local interconnect. We kind of figure out what's legal and what's desirable to put in a logic block. Then we have to choose where all those things, and RAM blocks and DSP blocks, so do that for all the blocks. Choose where to put them all. Okay, so we might have 10,000 blocks and we got 20,000 locations. Where do we put every one of these? And then route them. So basically pick which wires are we going to use, which switches are we going to use. All of these stages, so packing, placement, and routing strongly influence how fast the circuit is. So all of them are timing driven. Timing driven means each of these optimizers is estimating delay. Okay, so the packer estimates it quite crudely because it doesn't know that much yet. The placer has a pretty good estimate, and the router has a very good estimate of delay. They ask an algorithm called a timing analyzer that basically just goes through the circuit finding what are the speed limiting paths. Okay, what are the longest paths between flip-flops, and gives back information to the optimizers about what are the long paths, how long are they compared to other ones, and the optimizers now focus extra effort on those. So those long paths, the placement engine would now try to extra hard to put those close together, even if it pulls some other stuff apart. And yeah, that's very important for FPGA architecture evaluation, that those phases are timing driven, because they have such a strong impact on the speed of your design. Okay, and then when those are done, so if we were running Quartus, Quartus is similar to this, so you change the names of which tools it is, but it goes through the same basic phases. Quartus basically is going to produce a bit stream here, so it'll go to a programmer. Okay, inside, and it will also tell you what's the delay, and it'll tell you what the power is. VPR doesn't bother programming it because you're just estimating an architecture, so you don't need to program it. It does one last thing. It also estimates the area. So Quartus doesn't do that because the chip's done, right? Like, and you don't care, right? You paid a certain amount of money for that chip. Doesn't matter what its area is. In architecture evaluation, we actually care. So it basically applies all these area models to all the circuitry in your design and architecture, and gives you these final numbers. Okay, and then the last thing it does is these algorithms basically adapt to what is the architecture. So Quartus and Vivado have a certain number of architectures that are built into them, and they know how to optimize very well for those architectures, like ARIA 10 and Versal and so on. So VTR is a bit different. It basically, you give it a human readable architecture description. So there's a language to describe does this FPGA look like, and that language is, yeah, a human can type it in. And then the first phase of the CAD flow is actually an architecture generator that takes this description that might be 100 lines, or it might be 1,000 or 5,000 lines, depending on how complicated your architecture is. And it turns it into the really big data structures that define an entire FPGA. Okay, so for example, if there's a million blocks in this, it produces like a map of where are all those million blocks. If there's 100 million wires and 500 million switches, it produces a graph with 100 million nodes and 500 million edges. So this is a lot easier to specify than basically the really big data structures. So it builds those for you. Once it's done that, it has this architecture database, which is basically similar to what you'd have in Quartus or Vivado. So in Quartus and Vivado, they have those really big files for all their chips. But again, you wouldn't want to type that in by hand. That's why you can just describe the architecture at a higher level of abstraction, and this architecture generator bridges the gap. Any questions on that? I know it was kind of a high-level overview of this. You'll actually use this tool in assignment 4. Okay, so you're under assignment 3 where you're writing a RAM mapper. The RAM mapper is basically a part of this packer. Okay, so you're writing a mapper that decides for the RAM part of the architecture, how can I put this into the RAM blocks that exist on the chip? So that algorithm exists inside VPR, it also exists inside Quartus. You're writing your own. Okay, so that's what assignment 3 is. Assignment 4 is you're going to basically use this tool. So I think by the end of assignment 3, you'll be like, I'm done writing CAD tools for a while. And for assignment 4, it's a bit smaller scope. You basically answer some questions by running an existing tool. And this is the one you'll run. Okay, so no questions on that. I'll go on to some results that were generated from this flow. So this flow has been enhanced many times over the years, but you're going to see that a bunch of the papers that we are going to look at used various versions of this flow. Okay, so the first one is kind of a classic study by Professor Rose and his grad student Elias Ahmed. So Professor Rose is a professor here at U of T. And they looked at the kind of two of the key questions that I laid out at the start of this. How big should your LUT be, and how big should your logic cluster be? So the first thing they did is, let's just take simple logic blocks. Forget all this logic cluster stuff. Let's just say it's single lookup table. So what we just did now. But instead of saying it's a 4 LUT, maybe it should be a 3 LUT, maybe it should be a 7 LUT. We don't know what size of lookup table we should use. So this is one of the results from their paper. So they're just looking at a logic block that is a single LUT plus flip-flop. And on the x-axis, they're changing the lookup table size. And this curve here is the area per cluster. And a cluster, again, is just one lookup table plus flip-flop. So it's showing what we worked out just by transistor counting, that the area per logic block goes up exponentially as you increase the size of the lookup table. So this curve is going up really fast. But at the same time, the number of lookup tables you need is actually going down, because the synthesis tools can pack more and more functionality into one of these bigger lookup tables. They don't need as many. And that's what this curve is showing. So you need fewer lookup tables for their benchmark circuits, but each one of these logic blocks is bigger. Okay, so when they put all that together, just count up how many of them you need and what was their area, including all their routing, this is what they get. That their best area actually occurs at a lookup table size of 5, with 4 and 6 not being too far off. So if you have too small a lookup table, you need a whole lot of them, and each of them needs some routing. So you wind up with something that's inefficient because you have too much programmable routing. As you go to bigger lookup tables, you don't need as much programmable routing because there's much fewer blocks to connect. But the cost of the lookup tables eventually starts getting very high. So a 7-input lookup table is also pretty inefficient. But they found a pretty range, that 4 to 6 was pretty reasonable for area. Okay, so then they said, well, maybe we shouldn't just put one lookup table in, though. Let's try making bigger logic blocks where we do exactly what we talked about at the start of this presentation. Basically, we have a logic cluster. It has a lookup table plus flip-flop, or n of those, along with some local routing. That's what this is. And some number of inputs we can bring in from the outside world. And we can get all the outputs back out to the regular routing. And all of those outputs also can feed back into the local routing. That's our logic block. It's embedded in an island-style FPGA. Okay, so between the logic blocks, we have this segmented routing, island-style. Within the logic block, it's like we have a one-level hierarchical FPGA. Make sense? And they're going to basically look at area, delay, and yeah, it's common to look at area delay product for the reasons we talked about earlier. It's like the opposite of throughput, so it's a good way to put together trade-offs of area and delay. They have to decide, and they're looking at number of blocks per cluster, lookup table size, and how many inputs they bring in. They want to know those values. They have to choose a routing architecture to do this. So, I mean, ideally, maybe they would retune the routing architecture for every single logic block architecture, but the amount of computation and time that takes starts becoming extreme, right? So Elias was a master's student. He might have wanted to graduate eventually, so he didn't do that. Instead, he said, well, it's known that a good routing architecture, length 4 routing wires work well. Previous studies had shown that, so I'm going to make all my routing wires go past 4 logic blocks. And I'm going to make this local routing a full crossbar. And in terms of how we build our wiring switches, there are a few different ways we can build them. He built half of them with pass transistors and half of them with tri-state buffers. And previous work has shown that this is a reasonable choice too. And this was all done a while ago, so it was a 180 nanometer process node. So there are a bunch of embedded assumptions in a study like this. The process technology, how the routing works, et cetera, which means some of these conclusions might change over time. Okay, so one of the things he has to do is he has to come up with a bunch of delays that he tells the CAD tool about. So this shows the signal path going in and out of a cluster. So we have these routing wire segments, this island style routing that's all around our logic blocks. If we go into the logic block by going through an input port, so one of these routing muxes to get in, he assumed an inverter here that isolates the routing wire from this mux. And it turns out that's actually really hard to lay out. So that's, he's not the only person who did that. But once I was working on commercial FPGAs, I realized this doesn't work all that well. Okay, it wouldn't affect his conclusions much, but it actually shows it's complicated to do these studies because you've got to do so many things, like design the circuitry and make sure the CAD tools work well. So anyway, wouldn't have a big impact, but if you actually go build this, leave that buffer out because it's really hard to lay out. Goes through a mux, there is a buffer there, that one's reasonable. There's local routing. The local routing is built using multiplexers as well, and it forms a full crossbar. Then there's a K input lookup table. Optionally, you can go through a flip-flop. And then you can pick one of those two signals to come out, and there's a buffer here driving you back to the local routing, and another buffer here driving you out to the general routing. Overall, it's a pretty reasonable electrical design. This one buffer here is, the one that probably should be left out, and future studies did leave that one out. I think there's a question. Yeah. Yeah, so they're in, so you don't put this in like your benchmark circuit. This is like the electrical design of the FPGA. Okay. Yeah, it's basically to isolate capacitance in order to improve speed at the cost of area. The reason this particular one, it turns out you need a bunch of these inverters, like quite a lot of them, mixed in with the general routing wires. That turns out to be hard to do, and it's not a great area delay trade-off. Does that make sense? But the rest of this actually is pretty close to the way that the FPGAs that I know of are actually electrically built. Okay, so after they kind of build this and spice it, so they extract all these delays, they get area models, they basically do some CAD experiments to see, okay, what can we get out of this? Now, that was kind of the cost. What are the delays? What are the areas? Now, what's the benefit? They needed to figure out how many inputs they should build to this structure. Okay, so the number of inputs here is I, right? How many of these muxes are they going to build? And the number of inputs they bring in also affects how big these multiplexers are, like the local routing crossbar. So they'd like to make I as small as possible. It's going to make this more area efficient. And smaller muxes are also faster, so it's good for speed too. But they have to see, well, what does the CAD tool need? If they just made the number of inputs too small, you'll just have a whole bunch of lookup tables that you can never use, and that's also kind of pointless. So what they did is they just looked at the output of the packing stage, the stage that's actually making the logic blocks across their benchmark circuits, and they varied. Well, this is actually work from a paper to reference, which is they're basically working out how many inputs they need in order to be able to use almost all the lookup tables. So to use 98% on average of the lookup tables in a logic block, they needed to have basically a gradually increasing number of inputs. So it makes sense as they put more and more lookup tables into the logic cluster, they need to make more inputs to it, but they don't have to make them all available. So what they found fit well was if they made the number of inputs equal to k divided by 2 times n plus 1. So that's about half of the number of inputs to the lookup tables, right? So each lookup table has k inputs, there are n of them, so the total number of inputs you might want is k times n. They didn't build that, they built about half that many. And they found that if they did that, that they could basically use 98% of their LUTs on average. And it was easier for them to do this experiment rather than change I and do experiments all the way through placement and routing. So it's probably a reasonable thing to do. Now this actually says that the number of inputs they need to a logic cluster is growing linearly though, with the number of lookup tables they put in it, which would imply relatively poor locality from Rent's rule, right? So Rent's rule says this implies a Rent exponent of 1. So only putting half of the, they're only putting half the inputs in that is the maximum. But Rent's rule says that this should probably grow sublinearly, right? Like it should maybe be n to the 0.7 or something. Part of it is that they're trying to use 98% of the logic, which means they don't really want the average number of inputs. This is a graph for LUT size 4, and it shows the average number of inputs goes up more slowly with cluster size than the maximum. Okay, so they're kind of trying to build enough inputs that they can pretty much always use these logic clusters. So they wind up building somewhat more inputs than Rent's rule would predict. And maybe that's not the best choice. You know, it's possible that if they built somewhat fewer inputs and just accepted sometimes they can't use all the LUTs, that they'd wind up with something that's more area optimized. But this is not an unreasonable thing to do. Does that make sense? Okay, so now that they've done their electrical design, they've picked the number of inputs per cluster, they go off and do a whole bunch of CAD tool experiments. So this is showing how much area is inside the clusters, okay, across a suite of benchmarks. So it's not all the area, it's just the area that's inside the cluster. So lookup tables and local interconnect. And this is a cluster of size 1. A cluster of size 1, and on the x-axis we have an increasing lookup table. Okay, so a cluster of size 1 doesn't have any local interconnect. So the area inside the cluster is pretty small. As they go to larger and larger numbers of lookup tables that they put inside of a bigger and bigger logic block, the total area inside the clusters just keeps increasing. And as they go to bigger lookup table sizes, the total area inside the clusters keeps increasing too, because they're making the logic elements bigger, they're adding more local routing, et cetera. Okay, so this makes sense, but it's not the whole picture. Because they also have to look at, well, what's the area between the clusters, right? All of this routing hooked them together. And basically it's showing the exact opposite trend. This is like this top line is a size 1 logic cluster, so no local routing. And as they go along this way, you're getting bigger LUTs. So as they make the LUT bigger, they need less routing between logic clusters because they don't need as many. As they make the logic clusters bigger with more local routing, again, that removes pressure from the general routing. They don't need as many logic clusters, they don't need as many routing channels, et cetera. So they've got two competing trends, right? Like these two graphs look like mirror images of each other. So to get the full picture, they have to add them together, and that's what this graph is. So this is looking at just clusters of between 1 and 5 lookup tables. Okay, so this is a cluster of size 1 right there, and then a cluster of size 2, and then clusters of 3, 4, and 5 down here. And then again, we're going across different lookup table sizes. So, okay, so what are we seeing? This is the total area, again, has a minimum around a lookup table size of 4 to 5. And moderate size logic clusters are good. Okay, so they are saving area but with this local interconnect. Okay, because the case with no logic cluster, a single LUT is up here. So it's not as optimized for area. Okay, this is the other half of that figure. These are the bigger logic clusters. And again, the minimum is around LUT size 4, with LUT size 5 not being too bad. And it's kind of hard to tell from this diagram, but this is like a cluster of size 6 right there. So they found cluster sizes of 6 to 8 were good, and lookup table size of 4 to 5 were good. Those were good trade-offs for area. Okay, then they looked at speed. So people care not just about area, but speed too. So again, lookup table size is going up this way. This is the average critical path delay. So it's like the opposite of speed. Higher is worse. As they go to bigger lookup tables, delay is going down. Okay, so their benchmarks are getting faster. And as they go from, this is a cluster of size 1, so no local interconnect. And this is a cluster of size 10 down here. So basically, bigger clusters are making things faster. The local interconnect's pretty quick. The bigger they make the logic cluster, the more connections they capture on this local interconnect, so it just keeps getting better. Okay, and then we care probably if you were to pick one metric you care about for an FPGA, you'd pick area delay. Right? You can make a small FPGA, you can make a fast FPGA. People actually kind of want both. So area delay gives you a good metric for that. So let's see, this is again cluster size 1. So it's not as good. So the fact that the area delay product is significantly lower down here means these logic clusters are useful. What size is best? There's a whole bunch that are pretty similar here. That's basically cluster sizes of 4 to 10 lookup tables. They're all pretty good. There's small differences, but they're more commonality. And there's also a pretty broad minimum in LUT size, right? So between 4 and 6 inputs all look pretty good for area delay. Okay, so if I was to summarize that, so for LUT size, a bigger LUT captures more logic, and you need fewer of them in series to implement your design, so your critical path goes through fewer lookup tables. That also means it goes through there are fewer connections that have to be routed between them. So it doesn't just help that you have fewer levels of logic delay, you also have fewer numbers of routing delay to add up. Now the lookup table itself, electrically, it is getting slower, so you need fewer of them in series, which is good, but the lookup table itself, its delay is gradually going up. And it goes up linearly in K, because you need another stage in your pass transistor tree for every input. And the bigger problem is that the area of your lookup table is going up exponentially in K. So that's why you start seeing, 7 starts going up reasonably quickly, right? Like you can't push this too far. Cluster size, so bigger captures more signals in the local routing and reduces general routing demand. So that's good. In this case, their local routing was a full crossbar, so its area is growing with n squared, which means they can't go to really big clusters. It starts becoming not good. And the local routing, because it's built with muxes, its delay is also increasing as these muxes get bigger. Also, the wires inside that form the local routing are also getting longer. So the local routing, as you make the cluster bigger, you capture more and more connections in the local routing, which is good. But the local routing itself is getting somewhat slower. So the gains of capturing them is going down some. And your area eventually starts to become not good. So you can't push either of these too far. Let's see. So yeah, so they did actually like a very thorough job of this, right? Because they used a full CAD flow, detailed models to evaluate all this. If you just cared about delay and didn't care about anything else, you would go for a really big lookup table like k equals 7 and a really big cluster, n equals 10. But you'll pay a lot of area for that. So for best area, a lookup table of size 4 was the best, and cluster sizes that were still pretty big were good for that. And if you had to balance area and delay, you had a broad minimum. Lookup tables from 4 to 6 inputs and cluster sizes from 4 to 10. Even though these ones, you've got a broad minimum here where there's not much difference in area delay, the 6 LUT is actually still significantly faster. They found it was 14% faster, but it was also bigger. And the 4 LUT, the 4 LUT was slower, but the 6 LUT needed 17% more area. So area delay product, it was close, but it was in a different point. It was faster but larger. Does that make sense? Yeah, so one thing that is, there are many things that can change. This is a very useful study that answers a lot of questions. But some of these questions may not stay perfectly answered because process technology changes are increasing wire resistance. CAD tools are gradually getting better. So some of these answers will probably be somewhat different if you did it again. But the broad trends are probably still the same. Does that make sense? Yeah. Yeah. Yeah.
Does that mean, like for a mass area design, like we require like more clusters and
Yes. Yeah. So if you use k equals 4, your logic cluster takes less area, right? Your lookup table is quite a bit smaller. If you use like n equals 6, like the area of your logic cluster and it's all its routing, might be half what it would be with a k equals 7 and n equals 10, or maybe less than half even. But you'll need more of them.
Yeah, does that mean like at the end, like the area will be like larger?
No, they account for that. Like when I say that the 4-LUT, like the 6-LUT took 17% more area, that's accounting for the area of the FPGA that you had to build to accommodate all these benchmark circuits. Does that make sense? So in other words, if your logic block is more capable, you don't build as many of them. You just build as many as you need for the circuit. So it's captured in their area model. So they're actually modeling, for commercial FPGAs, you make an FPGA family, you might make 7 or 10 variations, like a small one, a medium one, a big one, a really big one, 3 more I don't have names for. So you kind of, when you're designing your circuits, you have to kind of pick one of those. Like they're discrete, so you pick one that's going to be pretty full but not completely full. In architecture experiments, we usually don't do that. Instead, we just say for every benchmark, we'll make an FPGA that is basically the right size for it. It's like we make like a square grid that just barely fits that design. The reason is you get less round off. If you were to say I only have 5 FPGAs, you might have a lot of designs where they go from using 83% of the FPGA to using 76%, but they still have to use that FPGA. That just kind of adds noise to your experiments. So when you're doing architecture studies, you usually neglect that. You just say, I can make any FPGA size I want, and then I'll come up with the area that this benchmark circuit needs in that FPGA. Does that make sense? And that is essentially the continuous approximation to what you end up building, right? Like if you had infinite money, that's exactly what an FPGA vendor would do. We built you 1,000 FPGAs, so you can always choose the exact right one. They're never going to do that because the NRE is insane, so you have to round off. But that round off is not useful in architecture studies. It just adds noise. Does that kind of answer your question? Okay. So in the last 7 minutes, I'm going to see how far I can get through fracturable LUTs. How many people have read this paper already? Okay, a few. And if you haven't, I think I gave you a few more days, so probably these slides will make it easier to answer the questionnaire. So this could be a good one to do. Okay, so this is about Stratix 2. So Stratix 2 is, it was a major change in the logic fabric of FPGAs. So until about 2004, 4 LUTs were dominant. Okay, so based on some earlier studies that said that 4 LUTs were the most area efficient. But other studies had also shown, like I just showed you, that, well, the study I just showed you was done around the same time as Stratix 2. But it was known at this point that 4 LUTs were the most area efficient, 6 LUTs were the fastest, okay? So one of the goals of the Stratix 2 architecture was, could we have the best of both worlds? Could we get the speed of a 6 LUT architecture but reduce its area costs so we didn't pay any penalty for that? Okay, this is some data from Quartus that was kind of motivation for that. So this is showing how many inputs you use in various, for various lookup tables across a suite of benchmark circuits. So if we tell the synthesis tool that we have a 4 LUT architecture, Okay, so it'll never make a more than 4 input lookup table because it won't work. But it makes, more than half of the lookup tables are using all 4 inputs, but some are only using 3, some are using 2, a few are even using 1. You might go, well, what the heck are you doing with a 1 input lookup table? It's usually between registers, for example. You're just going through the lookup table to get to the register, which does happen sometimes. I have a shift register, there's really nothing for the LUT to do. It's just going to pass the data through to the flip-flop. Some of the reasons I might get 2 input lookup tables, we haven't talked about this yet, but when you get into adders often make small lookup tables. And we'll get to that probably next lecture. And sometimes you just don't have enough logic between flip-flops. This is kind of a special case of that, where you might have just a flip-flop feeding a flip-flop. So there are a bunch of reasons why you don't actually get all 4 LUTs in a 4 LUT architecture. And it gets worse as you go to bigger LUTs. So this is if you say, I've got 5 LUTs. Now it turns out the synthesis tool only is able to make, fully use 45% of the LUTs, and the rest are actually only using a fraction of their inputs. And with 6 LUTs, it's only using about maybe 35 or 40% to their full extent. And other times, it's only using some of the inputs. When you're using some of the inputs, it's painful. Like, it works, but you basically built a LUT that is exponentially bigger, right? Like the 6 LUT took you twice the area of the 5 LUT. So if you're using this 6 LUT as a 5 LUT, you're like, the LUT itself is twice as big as it needed to be. And it has 1 extra routing port, which I also paid for. So this is kind of a waste. Okay, so the idea of Stratix 2 is, well, can I make one hardware structure that could either be a big LUT or multiple small LUTs? Because if I could do that, then when I need a big LUT, I'll tell the synthesis tool, make a big LUT. But when the synthesis tool makes me some small LUTs, I could pack more than one of them into one of my big LUTs. And this would be good, right? This would save me area, but I'd still get the speed win. There's a speed win of using big LUTs because you need fewer of them in series, and that reduces the number of routing delays you have on the critical path. So that was the idea. And the number of LUTs they wanted to do, in theory, you could decompose a big LUT into a bunch of little LUTs, but what fracturable LUTs try to do is decompose a big LUT, when it's helpful, into 2 smaller LUTs. Okay, so this is the first option that the paper looks at, which they call a composable LUT. Okay, so the key insight is that big lookup tables have little lookup tables inside them. It's kind of like a fractal structure. So I've got a 4 LUT here. So you see 4 inputs. I got another 4 LUT with 4 different inputs, another 4 LUT with 4 different inputs, and so on. If I have one more input up here, and it selects between the output of this 4 LUT and this 4 LUT with this mux, that's a 5 LUT. And down here, I do the same thing. One more input that controls this mux. So now this LUT plus this LUT form a 5 LUT. And if I take one more input and bring it in, and it controls one last 2-into-1 mux, I have a 6 LUT output. Okay, so this composable LUT, actually can do a lot of things. Okay, it can be a single 6 LUT, but it can also be 2 5 LUTs, or it can be 4 4 LUTs. Does it make sense? So sounds great. Do you see any issues with this? What do you think? So you mean like this input to the output is going to be faster than, say, this input to the output? Yeah, that's actually fundamental with all LUTs, though. So like if you actually look at the Cordis timing report you get carefully, you'll see that different inputs to a lookup table have different delays, because if I basically look inside this 4 LUT, it's built out of a tree of pass gates. So whatever is controls the first level of that has the longest delay. Whatever controls the last level has the shortest delay. And actually the CAD tools exploit that. So in the routing phase of Cordis, it actually is routing all your signals, and it actually also simultaneously is trying to get those signals, if they're critical, to the fastest LUT input. So it's a good observation, but it's not really, it's kind of just fundamental. It just is always there. Yeah? You are. Why are you wasting area? So. I see. Okay, so you're saying this could be wasted, right? So that's true. If I use the smaller LUTs, I'm going to waste this. But this is small, okay? So these 4 LUTs we just saw have, we added up all the transistors. It was a lot of transistors. These are 2-to-1 muxes, 3 of them, right? I can make 2-to-1 muxes with a couple of pass transistors and an inverter, for example, which is like 4 transistors. So this is pretty small, right? Even if I make these pretty big for speed, the area of them is very small compared to this. And the area, remember, is not all about logic. It's also about the programmable routing. So the area of this is pretty small. But there is a problem with this. This isn't actually what they did. What do you think? Yeah, compared to just building a 6 LUT, you could say, well, if you think of a 6 LUT, you actually have all of this. Okay, so you say, I didn't add anything, right? All I did was bring some signals out. So that sounds great. Except that then you start counting what happens to programmable routing. A 6 LUT would have a single output to connect up to the programmable routing. We've actually made 7 outputs. A single 6 LUT would have 6 inputs, right? So that's 6 inputs. We've got a lot of inputs here. I think 19 inputs. Okay, so each of these is going to require those muxes to the routing. So if you only think about the logic block, you would say this looks great. But when you start thinking about the impact on the programmable routing, it's bordering on catastrophic, right? It's really expensive. So yeah, so I'm going to go 2 minutes over so I can show you what the alternative is. So okay, so what did they do instead? So they basically said, well, we're going to look at what a 6 LUT is. And a 6 LUT has 2 5 LUTs in it and a final 2-to-1 mux. So this is just a 6 LUT. I've just redrawn it. So they've already got this. So they said, okay, well, what do we want to do? We're going to allow this 5 LUT output to come out. Okay. So we do have one more output to connect to the routing fabric. That's going to cost us something. And if we want to use this in 6 LUT mode, well, then this output will be unused. If we want to use it in 5 LUT mode, then we basically just ground this. And normally the programmable routing, you can connect things to ground as well. If you ground this signal, then basically this top 5 LUT will come out here, and the bottom 5 LUT will come out here. Okay, so this can be used as 2 5 LUTs or 1 6 LUT, and the only cost was this extra output routing port, which isn't 0, but it's not catastrophic. This is basically, okay, so the Stratix 2 paper brought in this idea. What I'm showing you here is actually the way Xilinx does it. Okay, so Altera switched to a fracturable 6 LUT with Stratix 2. 2 generations later, Xilinx switched to a fracturable 6 LUT as well. But they did it in a slightly different way. They did this. They basically made their fracturable 6 LUT as cheap as possible. They added 1 extra routing port, but they can still use it as 2 5 LUTs pretty frequently. Okay. What Altera did is the same idea, but they decided they'd spend a little bit of area. They basically, okay, so this actually figure is not quite as clean as what I had in the other one, but they basically can take a 5 LUT and bring the signal out, because that's the 5 LUT, or another 5 LUT and bring the signal out. So they can use this as 2 5 LUTs, or they can use it as a 6 LUT by coming out here. Okay, so they've added an extra output as well, because if you actually look at the routing fabric, they do some reuse of their output ports. So they still only add 1 extra output port. Instead of having only 6 inputs, though, they add a couple of extra inputs. So they make 8 inputs. So the reason they add 8 inputs is basically when for Xilinx to use the 2 5 LUTs, they can't use more than 5 inputs combined. Okay, so that could happen if you got a 3 LUT and a 2 LUT. That's okay, or maybe you got 2 4 LUTs, but they share 3 inputs. So you can do that, but there's some restrictions. Altera basically decided, well, we want to be able to use this as 2 5 LUTs more commonly. So they added 2 extra inputs, which means to use it as 2 5 LUTs, you can use up to 8 inputs. So that means you can always do 2 4 LUTs, because 4 plus 4 is 8. Or you could do 2 5 LUTs as long as they share 2 inputs. Whereas Xilinx would have to have 2 5 LUTs that shared all the inputs. They're both reasonable solutions. The Xilinx solution is smaller, but you need more of them in the circuit because you can't use the 5-LUT mode as often or as powerfully. The Altera solution costs more area, but you get to use it more. And some studies we did internally when I was at Altera seemed to show that actually they were pretty close, actually. There are different trade-offs, but the overall efficiency was pretty close. Okay, and that's in there for today. Yeah.
The previous meeting that we had also mentioned that the guidance architecture, they could only get one bit out, they could only do one bit operation per.
Yeah, that's when we get to